I'll hang on a couple more minutes and hopefully Tony will join us, who's our first speaker in this session. What I can do is just run over some of the housekeeping things. Just to say, my name's Unique and I'm a staff tutor in Earth and Environmental Sciences, and I'm facilitating this session, and I've got Christine Mackay here who's helping on the technical side. And here's Tony now, which is great. So I'll just give Tony a minute. So just to say, welcome to this parallel session one. I know there's different rooms you can be in, so this is parallel session one, and there's going to be 3 talks in this room, one by Tony Hirst, then we have a talk by Nicola McIntyre and Geoff Austin, and then we have a final talk by David Bowers. Each talk will last 15 minutes, and there'll be a 5 minutes at the end of the time for questions. We can take questions orally if you put your hand up using the raise hand facility or in the chat box. Now, given the number that are attending the conference, and I can't know quite how many we might get in this room, and we may not be able to answer obviously all the questions in the time, but we will collect them at the end because the session is being recorded, and I will make sure they're passed on to presenters. So please don't worry if you do post a question and you don't have it answered. So I think without further ado, I'll hand over to Tony Hirst, who's from Computing and Communications, and he's going to give us a presentation titled Introducing RoboLab, an integrated robot simulator and Jupyter notebook environment for teaching and learning basic robot programming. Thanks, Tony.
Okay, good morning. Can I just do it? You can hear me okay? I'm going to assume that.
Yes, I can hear you loud and clear. Hopefully others can too.
Great. There is an option to play along either during the session or afterwards. There's an online demonstration on the service via my binder, and I've popped a link up there. Or you can try to run this environment on your own computer using Docker, which is a virtual machine application. That's actually the way that students run this environment, using a Docker container on their own computer. If you do try the Docker route, there is a small amount of authentication in place. You have to use the password "let me in," all one word, all lowercase, when challenged going into the environment. And I've also popped a link up there to a GitHub repository that contains all the source code, all the content associated with the TM129 activity. So, in the beginning was an application called RoboLab, a desktop application written originally for the Windows, written by my colleague John Rosewell. And this was created for a robotics short course about 20 years ago now, called T184, Robotics and the Meaning of Life. And the application provided a simple 2-dimensional robot simulator with a drag and drop interface where students would create a program in the middle panel of the environment by dragging commands from a command list on the left-hand side, and then they could execute the program and control the robot running in a little simulated window on the right-hand side of the screen. The robot program could also be downloaded to a Lego Mindstorms robot, which is a desktop robotics kit. And we used this environment not only to teach students on T184, but we also use the same environment for allowing students to program robots in an OU residential school, robotics engineering residential school. So the interface would allow students at home to run programs on their computer, or if they had a physical robot, they could download the robot and run it practically as well. And that was quite an important design consideration of that original environment. So that RoboLab application has been used in the TM129 level 1 block on robotics for many years, and we were in a position where we were updating the course. We wanted to update the software, We wanted to replace RoboLab. As I mentioned, it was a Windows application written for a very old version of Windows originally. We wanted to retain the original narrative and coverage of the activities. We wanted to move to a Python-style text programming language, and we wanted the application to work on an OU minimum specification computer. So there were a couple of additional constraints that I sort of brought into the mix. One was that I wanted the software to be delivered through a browser. Part of the reason for this is that it, in principle, can make the environment where the software runs on the back end independent of place or computing availability. So if you're accessing an environment through a browser, the server that makes that environment available could be running on your own computer, or it could be running on a remote service. So by making our software available via a browser, it means we could deliver it to students via a hosted server, or they could run it locally, ideally. I was also keen on exploring the use of Jupyter notebooks. I'll talk about those a little bit more in a moment. And I also wanted to try to retain the original sense of fun that had been designed into the original activities. The activities themselves, as I mentioned, originally we had this desktop application with the 2D simulator. The simulator supported robots with a range of sensor types. So there were touch sensors and light sensors, and there were a range of output modalities as well. So robots could play a pre-recorded speech message, or they could output a tone, which we could use as an alert. So if the robot achieves a particular task, it could then play a note to alert the user that it had completed this task. The original RoboLab environment included a range of charting tools, so that when robots running in the simulator collected sensor data, that data could be analysed using simple charting tools within the application itself. And there was also a neural network package that could be used for training and testing simple neural networks, and these could then be used to work with the robot. So I also needed to be mindful that we needed to replace the neural network application, which I'm not going to talk about today, and have that interoperate with the robot simulator. So I did a review of possible alternatives of tools that were available, other robot simulators, and I've got a short report on that if anybody's interested. And the most promising candidate was a web-based 2D simulator called F3 DevSim, which had a 2D environment. There was it ran through a browser. There was an editing interface for creating simple Python programs that ran within the browser and controlled the robot. And there was also a little output panel, so the program could generate print statements or logging statements and display various outputs as the program ran. The editor had got syntax highlighting, which makes it easier to review and check the state of your program, although there were no other debugging tools. There was a reasonable range of sensor types. There was a downward-facing light sensor. There was an ultrasound sensor modeled so that the robot could detect objects within raised up in the 2D plane. And there was a gyroscope sensor so that the robot could determine its angle of orientation. So that was an extra sensor over, and the ultrasound and gyroscope sensors were over and above the sensors provided in our original RoboLab environment, but we were lacking a touch sensor. The F3 DevSim simulator also provided motor and wheel odometry, so we could measure the state of the wheels, how far they turned forwards or backwards. And the language package, F3 Dev, is actually a set of Python bindings that would allow the program to be downloaded and run on a physical Lego Mindstorms robot. So in principle, anyone writing a program that runs in this simulator should be able to download it and run it on a physical robot, which was nice to have if anyone has got access to an F3 robot. So I took that idea of the F3 Dev Simulator and I started pondering how we might be able to make it run within a Jupyter Notebook context. For those of you who aren't familiar with Jupyter Notebooks, they're an in-browser read, write, execute environment where we can write text, styled text, we can write code, we can execute code within that environment, and we can display the outputs of that code execution. Jupyter Notebooks have been used in TM351, the data management and analysis course, for several years now, and notebooks are also going to be used in several upcoming OU courses across various faculties. So as an environment, there's something that students are likely to see more and more of. The notebooks themselves were originally developed for computational science experiments as a way of documenting, recording, and executing reproducible research. So the approach I took was that within the Jupyter Notebook environment, we could have the Jupyter Notebook itself as essentially in part a text document that would contain teaching material that would instruct students on how to work through the activities, as well as providing information relating to the activities. And we could pop up a version of the original F3 Dev Sim simulator within a widget. I put quite a lot of time into actually developing and extending some of the features of the simulator and wrapping it in an interface. So the interface that you see on the right-hand side of the screen now is a reskinned and extended version of the original F3 Dev Sim simulator. And that simulator ideally should be able to run as a standalone simulator within its own web page, although at the moment it's slightly tied into the notebook environment. So how does it work, or what does it offer? The simulator itself allows us to do pretty much everything we did in the original RoboLab environment. We can load in specified backgrounds to try and help manage screen real estate. We can hide and reveal various parts of the simulator display. When the robot's moving around, it's quite important to be able to tell where the robot has been. So there's, like the original RoboLab environment, there's a pen up and pen down mode, so we can draw a trace of where the robot's been wandering around the simulated environment. We can situate the robot at specific locations, and we can write and automatically run downloaded programs. So within the notebook environment itself, the way that the widget is controlled, we can configure the state of the simulator, what windows are open within the widget itself by pressing the buttons at the top of the widget to enable and hide various bits of the user interface. But we can also script the way that the widget is presented. So in the example there, within the notebook, there is a code cell. And rather than running code within the notebook, what the code cell there is doing is it's launching the simulator with a particular configuration. So it's saying that it wants the simulator to be displayed with the background panel open and with a specific information panel displayed. So this is done using something called a line magic, and I like to think of it as essentially it's like a little laboratory assistant that we can say we want the simulator widget set up in a particular configuration to run a particular activity. Now, the activities that the students run are to write code to control the robot within the simulator, and that's also done within a code cell in the notebook using a different sort of magic called a block magic. And here we say that the code we want to execute is code that is to be sent to the simulator and executed there. Now, in writing these robot programs, there's often quite a lot of setup that's required in terms of loading in various Python packages and creating various variables that we want to use in the program. And so one of the innovations in the way that we writing these programs is to use some magic that can preload various bits of boilerplate code before sending the code to the simulator where it's executed.
Tony, you have a couple of minutes.
Yeah,
and then a few minutes
getting
for
there now.
questions. Okay,
So,
thanks.
So when the code's downloaded, the students can use these preloaded magics that insert boilerplate code, and if they want to view the whole code program that's available within the simulator, they can do within the simulator itself. So there's an option to view the total program downloaded to the simulator, and the boilerplate can also be previewed within the notebook itself. In terms of some of the sensors that are available, the light sensor I've actually implemented as essentially as a simple low resolution 2D camera. So as the robot moves over the background, we can display the view from the sensors, left and right sensors, as two little camera views. So we can move the robot around the environment and actually view in real time what the robot is seeing as it drives over the background. We can collect data as we could in the original RoboLab environment and display it in a live inline chart. So as the robot moves over the background, logging its sensor data, that can be streamed into a live chart. And we can also grab the data from the simulator into the notebook itself and work with it in the notebook environment. Okay, so that's me done. A couple of minutes for questions, I think.
Thanks very much, Tony. If anybody wants to put up their hand and ask a question, please go ahead. Okay, Robert, do you want to go ahead and ask your question?
Yes, is it possible to run any of the old RoboLab programs in this new environment?
No, it isn't. No, the original RoboLab programs were designed using a different syntax and also supported different sensors, and the sensors that were implemented work in slightly different ways. So there's no clean way of translating between the two. I did replicate many of the original activities, but also because we've got new sensors involved and new modalities for the sensors, like the camera view, that also gave us an opportunity to create a new range of programs.
That's fine. I'm an AL on TM129, so I was wondering if I have to rewrite my tutorial, and I think I will have to.
Yes, yeah, it's a complete refresh.
Okay, thanks.
I can help with that if you want to get in touch.
Thanks very much. Thank you.
There's one question, Tony, I think in the chat box there from Kate Sim saying, have you taught the J presentation of TM129 and did you use this? And I tried it on the MOOC that P. Thompson was talking about. I don't know if you want to respond to that.
TM129, yes, this simulator was used in the J presentation of TM129. And TM129 presents twice a year, so the next presentation is starting any time, and I think the student use date will be, when will it be? Round about May or June, I think. So yes, it's been through one use. There were a few little issues thrown up, but touch wood, most of it seems to have worked.
Okay, thanks. And I think Brendan, do you want to ask a question, or we'll maybe make that the last question? And if there's any other questions, you put them in the chat box and I'll collate them. Thanks, Brendan.
Thanks, Fiona. Can you hear me okay?
You're a bit hollow, but I think if you speak up, it'll be okay.
Oh, it's probably on the wrong microphone. It's the Teams thing. Let's see if I can fix it. Yeah.
Right, is that better?
Much better.
Right, yeah, it's using my headset microphone. It's these things, they default. Right, yeah, Tony, I just wanted to ask about, you used the word magic a lot in your discussion. I just wondered what particular meaning does that have, or is that just part of the fun way of talking about things, or does it have an actual meaning in terms of how things work?
It does actually have a meaning. So the notebooks are actually running IPython, which is interactive Python. And interactive Python, IPython, has this notion of magics, which are commands that they're a bit like macros. So they're prefixed by 1 or 2 % signs, and they essentially sort of, they are macros, but you can think of them sitting slightly above Python.
Yeah, so it's a kind of a concise way of doing a slightly more complicated thing.
Yes, it is.
Yeah.
And also, I mean, it very much adds to the sense of the word magic is really powerful, because I realized that what I could do was I could create magics to script lots of things, like setting up the environment to do particular things, setting up the simulator to do particular things. And by calling it magic, I don't necessarily have to explain to students how it works, and they shouldn't expect to know how it works.
Yeah, no, that's brilliant. I really like that. Thanks very much. That was really good.
I think that's something that we could probably use as a general idea more.
Yeah. No, it's great. Yeah, it works on all sorts of levels in terms of technically it's helpful, but also just it's a good way of communicating it to the students. So I like that. Thank you. Yeah.
Okay, well, thanks very much, Tony, for a very interesting talk there. We're now going to move on to a talk by Nicola McIntyre and Geoff Austin, who are from Life, Health and Chemical Sciences and Swim, and they're going to give a presentation titled Demonstration of the SK298 Open Science Lab Interactive 3D Brain Model. So over to you. Thanks.
Thanks, Fiona. I think Geoff has to share his screen or share his desktop.
I am doing that now.
You've done it. Okay, so now I need to take control.
Yeah. If you just take control, whoever wants to move things.
Okay. Yep, so I've got control, I think, although I don't see how I can advance the slides.
Bottom left, or use the arrow keys on your keyboard.
That's not working. Okay, I might just have to get you to do that for me, Geoff, if
No
that's
problem.
okay. Okay. Great. Okay, so thanks, Fiona. So I'm Nicola McIntyre. I'm a staff tutor in the School of Life, Health and Chemical Sciences. I was a member of the production team for module SK298, and I'm going to be presenting today with you alongside Geoff Austin, who's from the swim team, and he was also involved in the production of SK298. And we're going to be talking to you about the new interactive 3D brain resource that was produced for this module. So next slide, please, Geoff. So first of all, I just wanted to give you a bit of background to the module, to give all of this a bit of context. So SK298, or Brain, Mind and Mental Health as it's known, is a level 2 neuropsychology module, and it tracks mainly health science students, although we do have quite a lot of psychology students at the moment. It introduces students to brain structure and the function of individual brain regions in order that students can then get a good understanding of the biological underpinning of various mental health conditions. This is particularly challenging, first of all, because the brain is complex, and also because of the difficulties that students have in understanding the relationship between the different brain structures. So the purpose of the model is actually to allow students to help students visualize the brain in 3D to see how the various areas actually relate to each other. Next slide, please, Geoff. So just a bit of historical, background to how neuroanatomy has been taught historically. So the types of images that you can see in the screen here are what are, oh, my mouse, actually, that was my mouse that did that there, sorry. Okay, it does work then. I'll not click on the screen. Okay, so the images that you can see in the screen here, these are the types of images that are used in our textbooks and have been used in the past, and they do have their place. But one of the challenges is that students would struggle to understand how this cross-sectional view of parts of the brain fits with the whole brain structure itself. So it's not ideal. ideally, students would have access to some kind of a real brain dissection. So in a BRIC university, students do actually have that. So they might have access to human brain dissections if they're medical students probably, or access to animal brain dissections. We don't have those privileges. Therefore, we can instead use brain models. And there are a number of benefits of the brain models. So a 3D brain model, be it digital or physical, can help students understand the spatial relationships of the brain anatomy. It allows students to dissect, in inverted commas, the brain without the need to cut a real brain, and it provides an asset that students can go back to time and time again for revision purposes. A digital 3D brain in particular can show individual parts, so it can show parts of the brain in situ or in isolation, and it can also give students some extra information on the function of those individual brain regions, because students need to understand that. And basically it allows students to carry out practical investigations at a distance with essentially a brain in their hands that would not otherwise have been possible. So previously at the OU, students, in the good old days, students were supplied with brain models. This is on various modules, including SD226. They were provided with these lovely plastic brain models, and these are like 3D brain puzzles, if you like. They came out, you could break them up into several pieces, and they were really good for students to get a feel for how these internal structures of the brain here, how these fit within underneath the surface of the main cortex of the brain. So really, really useful, very effective, but obviously costly. I have to say I've been trying to get hold of one of these for a number of years and I've not been able to do it. So a good alternative is a 3D digital model, and one big advantage of that is that it can be distributed at scale and have thousands of synchronous users. So a digital 3D model was produced for the predecessor module of SK298. So this was a module called SDK228, and this is the type of thing resource that students were given access to. So it was a slightly interactive model. Students could play around with it. They could click in brain regions and get information about those individual brain regions, but it wasn't rotatable, and it wasn't actually fully explorable. However, with the advent of WebGI, that has now enabled us to deliver a fully interactive 3D model. I say us, it wasn't me, it was the swim team, obviously. So this has opened up possibility of a new improved model for students on SK298. In terms of designing this model, there was a few things that we had to consider. So first of all, we were constrained in that we had to use a 3D brain package, which had already been purchased by the OU. We spent a bit of time looking at some of the freely available 3D brain resources that are on the internet to investigate what kind of features were desirable and what features we wanted were less desirable. So the kind of things that we decided we really wanted were that, first of all, the screens needed to be uncluttered and free from distraction. So that's to decrease the cognitive load for students. Some of the freely available tools online have various pieces of information, links out to other places as well, and that was something we did want to avoid. We wanted it to have a relatively realistic and natural three-dimensional look to it. So some of the models that are available have a real plasticky look to them. We wanted fine control of rotation of the brain in all planes, so that's so students can get a different perspective on a particular brain area that they're interested in. And we also needed it to be set up so that students could click on a brain region, get information about the function of that brain region, but equally to go to a list of brain regions, click on those, and then to be able to see that highlighted within the brain itself, and then to be able to rotate the brain to see exactly where it sits. What we really wanted was that the relationship between these deeper internal structures that I was talking about previously and the external features of the brain, how they actually fit with each other. And we needed it to be adaptable for each topic in the module. So each topic looks at different mental health conditions or neurodevelopmental conditions, and we needed to be able to adapt the tool for that. And also, finally, we needed it to be suitable for using for some outreach work as well. So we wanted it to be put on the Open Science Lab platform. I think it's over to you now, Geoff, isn't it?
Yeah, that's right. So as Nicola said, we had a 3D brain model that was used for a previous course, and all that was used for was for making some videos and just some clickable pictures, and that was as far as it went. Whereas now it's possible for a web browser to be able to display 3D objects and to spin them around and look at them. But the trouble is, even though we'd had this built-in model, it didn't necessarily do everything that we wanted. So, for example, it had a sagittal plane, but there was no coronal plane, so we had to build that ourselves. We had to slice through it and create this the front image there, because that just didn't exist. There were a few parts that the course team needed to refer to that didn't exist in this model. It was slightly more detailed than they had, so we had to add those in, place them carefully in the right places. So the models as they came were good, but they weren't perfect. But we were able to adapt it for use for the students. So the other issue that we found was that if we had this 3D model and we were sending students on the VLE out to this web page, say with the model in it, and then having to go back again, it was going to be a bit of a pain. They would lose their place, forget what it is they were doing. We'd end up putting everything into the 3D model system rather than having it in the VLE where it's meant to be. So what we decided to do was to actually break it up and have little bite-sized pieces. The same as you have activities in the VLE, a 3D model should be no different to that. So you can go through the text, see a 3D model, have a quick spin, have a look at it, a very cut down that's just for the context of that text, and then you move on and you maybe encounter it again later on. So one of the features, or it's in JavaScript, it's in a web page, so it runs in the VLE. It means it can run on a phone. We did have to check that the model wasn't too heavy to be able to be displayed on phones. If it's got too many polygons, it could slow it down. So we had to be a little bit careful of that. And because we had the model, we could use it for videos as we had done in the past, as well as for the interactive side. And because it's exactly the same model, it looks identical. So let's just have a quick look on the VLE. In fact, I'm going to do this page here. So this is the brain model being used just in a video, which is showing some of the odds and ends. We've got blood vessels, and then we fade to the sliced coronal view there that we made. So we can do it traditionally, same as that, but then further down here, we've then got an interactive 3D model, and we can make that full screen so we can have a nice big look at it, zoom in, zoom out, and then we can choose some of the parts to highlight and get some information about them around here. And we can click on various pieces as well to get some more information. And just have a freely rotating spinning brain, works with the keyboard as well. And then we can just pop that back into the page. And then further down, another video here showing different parts of the brain. And then here we've got another version, 3D model, showing the internal structures. And on this one, we can then switch between different views. We've got the sagittal view there with a few parts. And then when you switch to the combined view, you can see how that fits together, corpus callosum. And we can go to the internal view and just see that separately. We could have done more things. We could have faded away the rest of the brain when you're selecting a part. We could have exploded it. There's lots of other options that were there, but we felt this was nice and simple, nice and straightforward, and people could find what they needed. Let's switch back. So the other thing we wanted to do was to have this outreach version. So something that combined all of these various pieces that are scattered throughout the VLE into one place so that they could use it for revision. So it wasn't the main source of teaching for the course. That's in the VLE where it should be. But this outreach one is for other students on other modules. And it's also a way of just bringing everything together into one place. So let's have a quick look at that. So this introduced a little menu with loads and loads of items taken from various parts in the course. So I will switch over to that again. So this is on the Open Science Lab, which has got lots and lots of 3D and all kinds of exciting things to have a look at. But here we have a menu of various pieces. So we've got some of the other brains that we used with different structures that were being highlighted. Some of the LDS activities were also included. So this is actually very similar, taken from the original 228 course. And we have some other ones there. And then more structures. Okay. With some different parts that need to be highlighted to see what we're doing. So let's go on. So it's had a fair number of people using it. It hasn't gone on for a very long time, but it's been very popular. And we will go on. Other things that we could do with it, because we can have 3D models now in the VLE, we could do any 3D model. We've just been doing static ones, but there's no reason why they couldn't be more complicated and animated. And there is things like augmented reality and virtual reality. I have taken some of these models and put them into VR just to see that you can pick up a skull, rotate it around, examine it, put it back down again, throw it, kind of thing. So all of those features are possible. And there we go. Over to questions, I believe.
Bang on time. That was great.
Yes, keep an eye on the clock, yeah.
Very, very interesting. Thank you very much. So again, if anybody wants to raise their hand, if they've got questions, I think there were a few things there in the chat box, but I think Brian was maybe picking some of those up. But if anybody's got a verbal question, please put your hand up. Could I maybe just ask, you know, how students have responded to it? You know, how, you know, have you had good feedback from students about its use?
It's a really good question, Fiona. Okay, so we've been trying to get data on student interactions with this, with the resource that sits within the module website. It's not that easy. We're still working on it. So we don't actually know in terms exact numbers of students who are engaging with it and how long they're engaging with it and when in the module they're doing that. So that's still something that we're working on. We plan to get some feedback from students this year. And also the plan is now to incorporate these direct feedback questions into the VLE, which is now possible. I plan to incorporate those into the module for next year so we can get some more specific feedback from students.
That's great. Okay, thank you. Anybody else got anything they would like to ask? I thought it was fascinating, I must admit. I love playing with those things.
That's a question in the chat box here from Kim. We don't actually know who's engaging with the tool within the Open Science Lab. I don't even know if we can drill down into that information eventually. That's probably one for you, Geoff.
Yeah, there is on the Open Science Lab, certainly we can get a list of a number of users and go down as far as who they are and how long they've been looking at the brain for. So yeah, we can get some of that information out, and we'll be keeping an eye on that. We did a similar thing. I'm sure we're out of time for some skulls as well. We did some 3D skulls, doing a similar kind of thing, and that's been very popular because that's open to all, where we can look at skulls and measure them and do that kind of exciting stuff. So there's all kinds of things. Now we can do 3D models in web pages. Anything's possible. But certainly we can track how much students are using it, and we'll be keeping an eye on that.
That's great. Well, look, thanks very much, Nicola and Geoff, for a really interesting talk and also for a great demonstration. I think it's just great to see these things, you know, and how they're used with the students. So thank you. So we'll now move on to our last talk of this session, which is David Bowers from Computing and Communications with a presentation titled Evaluation of Game-Based Learning in a Level 2 Computing Module. Sorry. So over to you, David. Thanks.
Teams is still thinking. There we are. Should have a slide.
I can see your slides and I can hear you, so that all looks good.
Excellent. I don't trust technology. I'm only a computer scientist. Okay, what I'm talking about is the sort of evaluation we did of a game-based learning activity in a level 2 computing module on service management. The module is TM254, called Managing IT, the why, the what, and the how. And the first block is the why. Why do we need to manage IT? It's all about something called service management. And the point is that IT services include everything from internet shopping, search, sat-nav, 3D models in the VLE, Teams, whatever. And it is the services that users want, not the particular software that implements them. They don't care how it's done in the background. And the services actually need to keep going, not only for a long time after the software has been launched, but also if the systems or software change. That's what service management is about. And one of the points about service management is that it requires timely communication between several people that are collaborating on keeping the services going. They are essentially members of a functional team. And let's talk about game-based learning. Well, Wiggins, the reference is at the end, defines game-based learning as the intentional use of games or simulations for the purpose of fulfilling one or more specific learning objectives. What are our objectives? Well, we sought to develop students' insight into collaboration in the sense of focus on service management rather than on their personal empire. I'll say more about that in a moment. And also communication. This was an email mediated game, so they had to notice the relevant emails amongst the routine deluge and responding promptly to events as they arose. So the scenario was that we have a modern building with glass walls, with mastic between the glass panels. The machine room, the computer room, is in the basement. And the team member, and this is not really JLB, the team members are each predisposed to looking after their own local stuff. So the sealant starts to leak and break down. And what the team is supposed to be avoiding is an alternative cooling mechanism in the machine room where it ends up flooded. We've reported the game itself initially in the STEAM conference last year and also Computing Education Practice last year. The game is based on teams of 5 allocated on a first-come, first-served basis. The students sign up. They're anonymous. They don't know who they're working with. They just know what the other roles in their team are. And every member of the team receives 1 email a day. Most of them are just noise emails, but one of those 5 emails requires a response to an event, which can alter the evolution of the situation, avoid the disaster, or accelerate it. And because there's 1 email a day, if there's no response by the following morning, 3 o'clock in the morning, it's recorded as no action. This is to accommodate asynchronous students because we don't know when they're going to be looking at their emails and so on and so forth around their own working patterns. It's one of the problems and challenges, and I'll come back to the impact in a minute at the end. The game ends either when the disaster is averted or the machine room is flooded. The simulation is also provided as a separate freestanding simulation for those who cannot participate, which can be run several times and uses quasi-random selection of the responses so they can see what happens if different people do different things. There's then a question in the TMA seeking the students' reflection on the activity in the simulation and what they've learned about collaboration and communication. The evaluation, we missed the opportunity in the first presentation because of time pressures, and it wasn't really appropriate last year because there were other things going on. But this year we ran a short questionnaire using the RTSF tool at the end of the first block. And I've got the approval number there from the student research panel. It was completely optional participation, which of course means it was self-selecting and may have tended to attract those who had issues with the module. So this is always the risk with a self-selecting feedback session. We had about 205 responses, about 20% of the participants in the course. What we looked at with the general teaching approach, which I'm not talking about here, the realism of the scenario, would you really have a glass building with leaking walls? The use of asynchronous communication, that is email, the importance of effective communication and the need for a prompt response. One of those we succeeded with, one we didn't. The importance of collaboration rather than local focus, taking account of the anonymity, and the feelings, student feelings about the activity. We asked them to compare the activity in the simulator and also a few additional features. So looking at some of the responses, did the actual scenario behind the simulation seems realistic? And it was only 12%, 1 in 8 thought it was completely silly and unrealistic. All the others thought it was at least plausible. And a significant number thought it was horribly realistic and far too close to home. And when I shared it with support colleagues, they were had that view as well. How well do you think it helps participants understand the importance of effective communication? Well, this is slightly worrying. 30% thought it didn't really help at all. Whoops, didn't mean to go there. And that's something we have to consider a little. So it wasn't completely successful, not as successful as we would like. This was a question about the timeout. Did you ever find that you missed it? And here we have 62% never encountered the timeout. They'd always responded by 3 o'clock the next morning. And we had a significant minority, 32%, who had encountered it, but only once or so. And anyway, they probably only had one message, perhaps. 4% or so, half a dozen student respondents had given up anyway and were just ignoring the whole thing. In the light of their previous answer, how effectively do you think the activity drew attention to the importance of responding to emails in a timely manner? And this is where it shows that this activity did not develop that insight, because 61% thought that it didn't really help at all. There were, again, a minority who thought it did, but I rather think that is just not good enough. It's something we have to look at again. Then we turn to the idea of the collaboration. Now, the 5 actors in the scenario are things like the IT manager, the user manager, the building manager, and so on. And each of them was given a sketch brief of what how they were supposed to be reacting, and the brief always tended towards looking at their own little empire. And the point of the activity was you could only avoid disaster by working together. So how well did that demonstrate it? And again, half of the students didn't think it demonstrated it at all. About 48%, 38% thought it sort of did. And I'll just point out this one in the middle. This is team working. It is students, and it's never the students' fault that things go wrong. It's always someone else in the team. And we keep seeing that coming through, no matter how we try to minimize that impact. This was finally a question about, did they mind not knowing who the other players were? And here, there was quite a lot of concern. They would like to talk to the other members in the team or directly outside the actual activity. There was a sense from some of the comments we'll see in a moment that actually they wanted to kick some of those who weren't actually doing anything, weren't responding, to respond, because they were letting down the team, which I suppose is realistic. If you're working in a team and someone else isn't doing something, you might sort of say, is there a reason why you aren't doing it? Can I help, etc., etc. But it's this feeling of helplessness if other people aren't doing what they're supposed to do. Then we asked them about what they found most amusing and most irritating about the activity, and we had some fairly positive comments. I've said that there was one message each day to each participant, only one required a response. The other 4 were noise. There were random messages such as one gets in one's email inbox every day, and it made it more authentic for some. Some noticed how quickly things can take a turn for the worse if people take their eye off the ball. We also got some hostile reactions. Dishonest not to report these, but some of these are actually quite misleading. Really, this person had no idea why they were trying to do this. They were think that computing is just about coding. That's all they're here to learn about. Sorry, that's not what computing is about. Even programmers spend most of their time doing other things, and they perhaps haven't yet got the maturity to understand that there's more to computing than just coding. And this, I think, is one of the key ones. Some people actually got it and saw what the whole thing was about. Then on irritation, email timeouts. Now, this is actually hiding something which could be a problem. We found that several students reported that even though the emails were sent at 9:30 in the morning or thereabouts, they didn't arrive until about midnight. So something in the email chain was delaying them. Complaints that they didn't have enough opportunity to shape the outcome. I think that's something we can take on board and move forward with. And similarly, this one is too short, not enough to do, no real interaction with anyone. And I think that's part of the problem of having set up one message a day to accommodate our asynchronous distance learners constrains how much can actually be in the activity. This is a very common concern for anything we ask the students to do. It wasn't clear that if they missed an email, they weren't going to be marked down on it, even though that was spelt out quite clearly in the introduction to the activity. There's still some students who were worrying about it. Now, we saw on the previous slide, someone liked the noise emails about sandwiches being thrown out and all the rest of it, and some didn't like them. And indeed, in the first presentation, I had a student complaining very loudly that never would work email be used for personal communications. It was completely unrealistic. In 25 years in the army, he'd never noticed personal communication on his email. Could be something to do with the environment. Then the last 2 here pick up that, again, this feeling of teamwork, which is always seems to pervade teamwork, that they might be doing their part, but other people aren't. And that is a bit of a concern, but I think it's actually also part of the learning, it's part of the experience that you can't control the world, you have to rely on other people. We then asked them about how they felt the simulator helped, because the simulator, using pseudo-random selection of responses, weighted, so the most likely ones were, or the most sensible ones were more likely to be chosen. They could run that several times and see the outcomes. Did this help them understand things? Well, quite a lot of them found it helped, and quite a lot of them found it didn't. 33%, a third of them found it was still far too confusing. Again, we've got to think a little bit about that. Did they want any other game-based facets included? Leaderboards is something we can probably do quite easily. How many people have drowned the machine room or repaired the building in time? Direct but anonymous communication with other members of the group. Although most high demand for that, I'm loath to provide it because it actually, even if it were possible, because I think it actually misses the point of the activity.
Couple of minutes left, David. Okay.
Okay. Other points raised, several students reported delayed emails, as I've mentioned. Some students reported errors in the activity, but showing the wrong state of the various participants, but didn't give us enough information to identify when, or that emails were lost altogether, no game over message. All of these things shouldn't have happened, which is a worry. So what were our initial takeaways? Most students found the scenario at least plausible. Most students understood the challenge of picking out important messages in emails, so those were good. But fewer than half, only 38%, saw why it was important to collaborate, and quite a lot of irritation of others who weren't playing their part. More than half wanted to be able to communicate within the team. Very few were affected by the timeout, and so the activity wasn't really able to develop an understanding of the need for prompt replies. Several wanted more opportunity to respond, and although they found the simulator more helpful, some were confused by the whole thing. So concerns is missing emails and failures. The 24-hour pulse is not really effective, even though it's designed to accommodate our students. Several students were frustrated by others not playing their part, an activity not long enough for them all to feel they had participated. They at most had 3 responses they had to make, and usually only about 1 or 2. So possible actions, we might extend the activity with a quicker pulse, but there are significant development costs because it has to be written by or developed by someone in LDS. And it will also, it is a trade-off, a quicker pulse would lead to many more students missing the timeout. Perhaps reduce the team size so that the events are shared between fewer students, gain significant effort and costs, or perhaps focus more on the simulator and allow the students to make the choices at each stage rather than relying on the weighted random responses. And because it's data-driven, it's actually easier to extend than the main system. So for others, we've demonstrated the possibility of asynchronous remote game-based learning, but we need to be clear what the learning outcomes are that are sought. We need sufficient opportunities for participation. So in our case, that would imply fewer team members or a longer activity. We need some support to run. Much of it is automated, but there were often glitches and difficulty in changing the scenario and events unless the whole thing is data-driven rather than program-driven. You have to change the code in this example to make things happen differently. And the accompanying simulator was valuable. So those are the takeaways for you and the references. Questions?
Thanks very much, David. Really interesting. And I think I completely agree there with whoever somebody was saying about the feedback. I think so. Yeah, it's useful just to get all that student feedback, isn't it, and how these things work. And group work, I think, is a challenge for all of us. So I don't know if anybody else has got any questions. Do I see one hand up? Let me just go over here and see. Robert, have you a question you wanted to ask? Maybe that's a legacy hand from Robert. I'm afraid, J.S. Craven, I'm afraid I don't know your first name. Do you want to ask your question? Go ahead.
Oh, yeah, sorry, it's Joanne here.
Hello, Joanne.
Yeah, I just want to say, David, thanks for sharing all the feedback. So honestly, it's really useful. I was just wondering about the quicker pulse, because I teach on a maths course, and I was wondering about doing some kind of escape room as a long tutorial, so have the students in little groups and with kind of puzzles they have to solve. So I wondered, when you were thinking about the quicker pulse, do you think it's something that would work, that you make the game take, say, an afternoon and people just book, a slot that they want to do it in, or do you think because everyone's kind of asynchronous, it needs to be something that they can just dip into when they have time?
Well, I think this has been one of the big debates, and fundamentally, we find it difficult to do things. The received wisdom is it's difficult to do synchronous events. And I'm not sure whether we would get higher or lower uptake if we were to do it as a sort of interrupt-driven thing. So as soon as one response is given, the next set of emails goes out and so on. It would be interesting to explore that, but again, it means rewriting the program because of the way it's developed. Not my bit of the program, the bit that was done by LDS. The thing is that would then allow a much more complex scenario. This particular one has 18 events in it, which is not really enough to get your teeth into. If you had something which was running much more quickly, you could have many more events. It's essentially then a business game, a traditional type business game. It could be done. It would be interesting to do. It's how you would do it on a campus-based university. Whether it would work for OU students, I'm not convinced.
Okay, thanks.
I don't see any more hands up. There was one question in the chat box there. David said, did you share these results with students later in the year? Then they could reflect on their responses as a group.
Sorry, did I?
Did you share these results with the students later in the year?
What I've done, I've said this, so far I've shared the summary. Just put it up in the forum. But the assessment does, and they can reflect on them, but there's no encouragement to reflect on them in the assessment pattern, the module.
Okay, that's great. Thanks for that. Well, I think according to my clock, we're bang on time, which is great. I would just really like to thank our speakers in this session, Tony, Nicola, Geoff and David, for 3 very different but all very interesting talks. And I don't know if everybody would like to either put on their microphones and try and do an applause, or at least use the emoticons, because I just think everybody has done really well. It's always difficult in this environment. So thank you very much, everybody. There is now a 10-minute break, so please do go and get yourselves a cup of coffee or whatever. I always think it's always much more difficult concentrating online for these long periods of time, so please do get a break. And then parallel session 2 starts at 11:20, and you've got your links in your programme. And it's been great to speak to everybody this morning, and enjoy the rest of the conference. Bye.